Hi all, this is Mr. Yeager, starting with physical science. This is our first video with physical science. We're starting with basically a few videos on Unit 1 covering scientific method. This is all in preparation for physical science with the Georgia Standards of Excellence. I like to start out with a few units on, a few topics where basically we're understanding how to interpret the material, the data that we're going to be using, and again, this is stuff that just permeates throughout all of the units when we actually get into the physics and chemistry of it. So the first one I'm looking at is scientific method, where with scientific method, you probably have heard it numerous times with from all the other courses you've probably taken in science, kind of a set steps in terms of how we interpret things. So again, this is kind of my interpretation of that sum, using obviously what I've done in multiple years based on textbooks and other things like that. So here we go. So in my class, we just did a lab called Say Fred, where basically students have to figure out how to put a gummy worm inside a lifesaver without touching it. They can only use paper clips and trying to get it back onto a boat. So the idea with this is this allows students to understand they are using the scientific method in terms of any day interaction. I mean, any type of decision you're making it from a scientific point of view. So basically, something is presented to you, a question, some problem. You go, okay, what should I do about that? You basically develop a procedure, a hypothesis. Where do we get this? This is from your own personal experience and what you have learned from other people and from other things of how to try to approach it. So we create a procedure, a hypothesis, trying to solve this problem. That procedure is then your experiment that you're going to then do. So the experimenting is the actual action of doing it and seeing what happens. Then basically, you collect some data, you analyze that data, okay? You basically analyze it, you see what you could have done maybe better, okay? But you analyze it, okay? You see what happens with that. You go, hey, this could be even just you're driving to school and going, there's a lot of traffic on this road. Well, maybe I'll try again tomorrow. There's a lot of traffic on this road. Maybe I should try a different way to go. And then basically that's what you're trying to do. You're analyzing the situation. Once you finish, you obviously make a conclusion, okay? And it doesn't have to be where it's like, oh, I solved the problem. Here's my conclusion. It could be, you know what? I didn't get any particular answer with this. A conclusion just means that's the end of this particular experiment. But what we're going to usually do is go back and revise and retest it, okay? We're going to see it again. We go, maybe we should try it a different way. Usually with the Say Fred lab, they do it one way, and then I go, okay, can you think of another way to try to do it again? Now some are like, well, maybe since now I know what to do, I can do it faster. That's fine. Let's try that. See, maybe after some practice, you're even faster at it. That's true, but maybe we try a different method as well, okay? So, for the scientific method, again, this is very generalized. It could be different anytime you look up on Google or anything else like that, but essentially they're all the same. You have a question or a problem, you form a hypothesis, you experiment, you collect data, you analyze that data, and you make a conclusion, and then you review and retest it, okay? And again, it could be where we make a conclusion and immediately go, well, know what, I need to go back and try it again. And that's retesting and everything like that. Or while you're collecting the data, you go, know what, this is not going well, I'm going to scrap it right here. And you go back and start again and go, maybe I need another hypothesis for this. So again, this is kind of just an overall approach to it. It doesn't mean that you follow all 7 steps exactly, but it's like this is generally how our minds are working when we try to interpret how to approach something. All right? So now basically for this, I'm looking at let's go through some terminology with it. We got the hypothesis. Many middle school, elementary school, I feel like they just leave it as an educated guess. That's a good initial definition for it, but the problem is I feel like as students get older, they said it's an educated guess, I'm just guessing. Now again, any guess is not an educated guess. There could be a dumb guess with it. All right. So what do we mean by educated guess? It's something that an inference that you're testing. It's a logical guess of what you think is going to happen, okay, and why. All right. So it's not just something just out of the blue. All right. Why is there traffic here? There must be an elephant on the road. No, that's probably. I mean, yes, it's a guess, But oh my gosh, is that going to be obviously something that really happens? No. Okay. So, could it happen in the end? Yeah, yeah, it could. But it's not a good guess, obviously, for a day-to-day type of thing. So it's something that you can actually end up testing as well. I think that's the other thing, and I believe the EOC has moved on from this some, but we have to be able to test this hypothesis. A hypothesis is something that has to eventually be tested. Otherwise, there's no point to it. Okay, you can't sit there and be like, oh, the dinosaurs just died because of a meteor type of thing. Well, how are you going to test that? The only thing is, that can eventually be tested by looking at the fossil record and looking at when certain meteors have hit the Earth. But is that something that you can test in the classroom right now? No. Excuse me. So, real quick, let's just try to go through and make inferences. Inferences is something, excuse me, that you've done probably in English classes, etc. So, let's say you arrive at school late and everyone is standing outside the building. Okay? What's happened? Okay? What would be some guesses? Usually what I get is some people say that maybe, maybe there was a fire drill. Okay? Maybe there's a fire drill involved with it. Okay? So, that's a good guess because obviously from experience, when there's a fire drill, everybody's standing outside. Maybe it just happened before school started. All right? What could be another reason? It could be, hey, maybe the building's not open. I've coached before and I have all my players show up and they're just standing outside the locker room. I'm like, what's up? They're like, the locker room's not open. Oh, okay. That's basically the, guess that I would probably have for it. Okay? I'm going back and forth here. You walk into your house and smell a wonderful scent. This one is very, very much from experience because what one person thinks is a wonderful scent might not be so wonderful to somebody else. Maybe you like baked cookies. Maybe you like Indian food. Maybe you like, onions and things like that. Maybe that's like, ooh, that's a nice smell, type of thing. All right. Other people might not, but again, that's your inference from your own experience. After hypothesis, this is something we can now test, and this is something that you do have to have structured and controlled, okay? Something that you basically have, and you know what could be affecting something else, all right? So you're not going to just randomly go, hey, it could be this, and I'm going to test everything at the same time. No, we need to have everything else controlled and only test one variable, which then obviously we break down step by step through a procedure. We're going to come back and go through, there'll be a separate video on experimenting and variables and stuff like that later. Data, after you have your experiment, obviously while you're doing your experiment, you're collecting data. And again, with that data, you'll be putting it into, data is obviously the things that you measure or observe. You'll be putting them into data tables, you'll be making graphs. You're going to try to see what this data is trying to tell you. Okay? What is the data trying to say? What do we see? What trends do we see? What patterns do we see on this? And that can then, we'll use that actually when you're doing those trends and patterns, you are analyzing your data to try to develop the final step, a conclusion. Okay? We will again also come back to another video on graphs. Then we have conclusions. Conclusions is based on your data. I can't stress that enough. It's so frustrating to me sometimes where we do a lab, and this is all levels, not just physical science, but my AP physics classes and things like that. We do a lab, and students give me an answer, and I go, where'd you get this answer? They go, well, it was in the notes. Why are we looking at the notes? You've got data right here. Tell me what's happening with the data. Well, my data doesn't say what's in my notes. Too bad. Explain your data. Try to defend your data. Okay? It has to be based off your data. Otherwise, the experiment was pointless. There's no need for the experiment if you're not going to use the data that you collect. So it has to be based on the data. So, to kind of close this out, you're doing this every single day. All right? Anything that you're observing, that you're trying to develop an issue, how to solve that problem, you're thinking this scientifically critical way. Okay? It's not special to think scientifically. All right? You are thinking this all the time. Little kids are doing this all the time. When they want something, they try to figure out how can they get that. Okay, what method works? It might not be the best method because they don't know, they don't have enough experience to try to develop those good decisions with it, but they make a decision in the end. Okay, so these new ideas often promote the new experiments and obviously help us change old ones. Okay, this has happened over time. Sorry, I mean that goes back. Obviously, you keep going, trying things over and over again. But I like to say, like, people believed in what's called spontaneous generation, where they just thought bugs, insects just came from nowhere. It just pop, they're there. We obviously later learned that there's germs that are developed that grow, and that's where then leads to the flies and everything else like that. So again, one good thought, spontaneous generation, moved on to a better idea, one that basically said spontaneous generation is not very good, is not true, and leads us to germ theory. Evolution is another good one. Again, I just read a nice article about where, you know, there was an extinct flightless bird off an island of near an island of Madagascar. It wasn't Madagascar, but off the coast of Africa in the Indian Ocean, that basically re-evolved into this. I mean, basically, this extinct bird came back. How? There was a prior ancestor that ended up traveling over to this island, and over many, many years evolved into this flightless bird again. Okay? So there's actually a legitimate term for that where it happens for evolution. So again, there's good ideas that keep developing with that theory. And the other one I always try to say to make it more relatable is, think about what smartphones have developed over time. I mean, each time you get this new, you know, iPhone 6, Galaxy SE, you know, just keeps on adding more letters. It keeps on making it stronger and stronger, more fast and faster. We're creating better and better ideas, technology, based on experiments and based on what people are doing to create these more useful, efficient, smart technologies, even in homes and everything like that. Traffic, we got automated cars that are coming out. Obviously, you can see there's been plenty of failures, but that doesn't mean they're going to stop doing it. Okay, they're going to try to make the adjustments to try to make it even better. Again, this is something you constantly keep on doing, testing, revising, accepting new ideas. Scientific inquiry is scientific thinking. Basically, the idea here is that you have to be thinking about this objectively as best you can. And that's very tough. All of us have certain biases. Okay, you can see bias written out here. We all have certain biases. We need to overcome those and look at this as what is actually occurring here. And again, I mean, this goes beyond science too. I'm not going to get into it, but again, of being able to see other points of views and seeing what is good and not good about those, even of your own. You should get reviewed. Obviously, if you move on farther with actual scientific publications, they get peer reviewed. They go to people that know about this stuff, and they look at it and try to determine what's going on with it. Okay. For peer review, again, we're looking at an idea that, you know, before we accept it, we try to figure out what we can try to do and allow others to test it. We don't want to just leave it at ourselves. There's been plenty of scientists that have completely lost their reputation because they didn't get their work peer reviewed, and they just made some outrageous claims. So it's something that's worthwhile. Obviously, in class here, it would be like another student looking at your work. Okay? Obviously, Twitter is not a good place for peer review. It is, people always want to use it now, but it's not very good. All right? So obviously, you have these different journals that come out that publish this stuff, and basically that's where we are led with creating, obviously, hopefully, this good information in these experiments and the scientific method. All right? So that's basically it. Good intro for scientific method, and that's it. Thanks.